All right, let's talk about decision trees. These are very interesting and very important because they're so easy to understand and they're so powerful, especially when used in forests, which we'll do after this. So here we're going to we're going to use another famous data set, which is someone measured parameters of flowers. There's 3 families of irises, and they measured various parameters of the length of parts of the flower to separate them into categories. So here we're going to just show there are 150 instances in the data set, 50 in each of the 3 categories. And all right, that's what it's going to be. So we are going to classify them with a decision tree. And here you go. This creates a decision tree classifier with a maximum depth of 2. So it's only going to have 2 layers. So here's the information. So it's going to 3 petal length, petal width are the 2 parameters we got measured here. I think there was a third we didn't use. Those 2 parameters are going to be used to separate them into 3 categories. Might have been there's only ever 2, I forget. But there's 3 types of flower: Setosa, versicolor, and virginica. And it turns out that all you have to now the decision tree has been optimized to do the best job at separating the data. And the way you do that is you measure this thing called the Gini coefficient of disorder. And so the Gini coefficient measures how heterogeneous this is. In this case, we start with the original block. We have all the data, 50 in each category. So that is a high coefficient of disorder. This has not been sorted at all. It contains an equal amount of all 3 classes. But if all you do is look at petal length and split it at the length 2.45, if the ones that are smaller than that go here, and that perfectly picks out the Setosa class. You get all 50 of them and none of the others. So this is a Gini coefficient of 0. This is the perfect separation. So this first if statement has removed 1 category completely. Now the false branch, of course, has 0, 50, 50. So now it's got 2 of the 3 possible things. So the Gini measure of disorder has gone down from 0.6 to 0.5. But you still have more work to do. So now it takes the other parameter and sorts it by petal width less than 1.75. And if that's true, it goes here. If it's false, it goes here. And now you see you get 49 of category 1 and 5 of category 2. Here you get 1 of category 1 and 45 of category 2. So these are pretty good, but not as good as this. And so you have Gini of 0.1 and 0.04. So these are the 3 categories shown by colors that you can get with a depth 2 decision tree. And like I said this in the very first introductory lecture, like one great thing about decision trees is they're easy to understand. If you don't like what this is doing, it's very easy to understand why it made this decision. So you could adjust it. All right, and now we can display predictions. There are various ways this is one way to display it with that tree there. You can also do it in a 2-dimensional plot of the measured petal parameters. And there you see here's one length and here's the other. And you can see the first decision splits it this way and is 100% successful at picking these out. The next decision has to draw a line between these 2, and it has to be a horizontal line if you make it with only one if statement on one variable. And so it's done the best it can to separate those 2 categories, and it's not able to be perfect. All right, so now we can change the depth. Let's change it to depth 3. Depth was, that's the plot. Here we go. Depth is up here. There, depth 3. Let's run this one. Now you're willing to make 3 if statements and separate things into more categories. The first if statement is the same because this one works. The next one, we're going to have 2 layers of separation. And now you can see we can get down to, this one's got a Gini of 0. Here's a couple. So, you get a more interesting tree that does a better job. All right. So now we're going to make a curve and noise. We're going to do curve fitting with a decision tree. Okay, so here's a curve, the same one we used before, x times cosine x plus noise. 0.1x times cosine x, so it varies. And we'd like to model that with a decision tree. All right. Well, there it is. We got a decision tree of depth 2 here, and we can graph it. You can display the predictions here. And there you go. As you would imagine, a decision tree with depth 2 is like 2-bit number. It can only separate things into something like 4 layers. So it's really going to do a miserable job of stepping through that data. However, you can increase the depth to 6, say. So let's go up here and try depth 6. Okay, and now you've got quite a big tree here. So big it doesn't fit very well on the screen, many layers of depth. And now if we plot it, you can see now it does a much better job stepping through the data with all these horizontal bars. And then what was more fun is to just have unlimited depth. If you just let it use whatever depth it wants to, which is what happens if you don't set the maximum, then this is going to be ridiculous, of course. And now if we do the prediction, this is what I meant about overfitting. It has now jumped up to spike every single data spot. So it jumps up to hit this data point, jumps down to hit that one, jumps up to hit this one. If you have enough if statements, you can, of course, hit every single value perfectly. But what you're getting is not a real representation of the trend. You're modeling both the trend and the noise, which is not going to generalize. So that's a thing to understand. So that's the structure of decision trees.